Let me welcome you all to this course on advanced fluid mechanics. I believe that many of you have already participated in my earlier course on the basic fluid mechanics, and of course some engineering aspects of basic fluid mechanics. So here in the course of advanced fluid mechanics, it is not necessarily true that we will be going very advanced into many of the research topics of fluid mechanics, but what we will do is we will try to advance some of the basic concepts that we have learned, and in the process this will be like really a bridge course between a first level of fluid mechanics and a very advanced level of fluid mechanics. So this is neither a very elementary level of fluid mechanics nor a very advanced level of fluid mechanics, it is something which is a bridge course intermediate between these two. Now I would like to give you some idea about the course outline, in a sense that the course outline has already been circulated and you are already aware about what are the topics that we will cover, but I will start with something which is very fundamental and which is fluid kinematics. So this is a review of fluid kinematics. We have covered fluid kinematics in the first level course. So but at the same time I need to appreciate that there are many participants in the advanced fluid mechanics course who might not have participated in the first level course of fluid mechanics. Not only that, kinematics appears to be a very basic building block, because kinematics, what it talks about? It talks about motion. Now when it talks about motion, it talks about motion without referring to any kinds of forces. So that means that when we are talking about motion, we are essentially talking about various features like description of motion, velocity, acceleration, these types of things which eventually translate into the final equations or the well known governing equations of fluid mechanics that any advanced learner in fluid mechanics must be able to make use of and must be able to synthesize in the form of useful problem solving. So kinematics appears to be very important, and we will start with our first lesson on review of kinematics. Now as I told that there are different ways of describing motion, and two of those, one is Lagrangian, another is Eulerian. So this is description of motion. So Lagrangian description, what does it mean? Lagrangian description, what it essentially means is that you are tracking individual particles. So forget about fluid mechanics or solid mechanics, in mechanics of continuum these, or even in a non-continuum perspective also, these are very standard ways of describing motion. So Lagrangian means essentially tracking of particles. So how do you track particles? So basically you start with an initial position. So this is given by a position vector r0, and then this particle evolves with time. So currently this is the position vector r, so you are tracking the particle. and this r is a function of the initial position and the time t. So, this is the Lagrangian description. So far so good, but we have to understand that it may be extremely difficult and very challenging to track the motion of individual particles, as a fluid is a continuously evolving medium. So, fluid is not something which is under static condition is of great importance. So, fluid, mostly in fluid mechanics, the major part is fluid under motion, and when the fluid is under motion, that means the particles in a fluid. So, what do we mean by conceptually particles in a fluid? So, by particles we do not mean molecules or these kinds of things. So, what we mean is essentially some tracer elements in a continuum perspective which are neutrally buoyant with the flow. That means a particle, a tracer particle which if put in the flow will move passively with the flow. It does not have any density difference, so it will not have any segregation from the flow, it will just move passively with the flow. So, if such kinds of particles are there, these particles will evolve arbitrarily and in a very complex manner in a very complex flow field. So, it is very difficult to have this Lagrangian description. So, as an alternative what we can do? We can go for something which we call as Eulerian description. So, Eulerian description is something like this. Instead of focusing on a particle, you focus on a specific region, or basically what you do is you sit with a camera and focus on a specific zone. So, let us say for example this is a pipe. So, in this pipe let us say you are interested to study the motion around this zone. So, what you do? You sit with a, first you identify this region, across this region numerous particles are coming in and numerous particles are going out. So, you are not really bothered about which particles are coming in and which particles are going out. So, what you do is you fix this zone which is your so called control volume. Then what you do is you study the flow around this control volume. That means what flow is coming in and what flow is going out. So, some fluid is coming in and some fluid is going out. Now, you do not care about which particles are coming in and which particles are going out. What you are interested to calculate, and we will see how you calculate it, that what is the so called velocity of flow or acceleration of flow, these kinds of terminologies. So, this is a little bit confusing term, velocity of flow. So, velocity of flow at a point, what is that? That is essentially velocity of a fluid particle which is neutrally buoyant at that point in the flow field. So, you want say at a given position you want the velocity. So, the velocity is a function of what is that position at which you are focusing your camera and the time t. So, see, in the Lagrangian description you have the initial position of a particle important. Here in the velocity description in the Eulerian perspective you do not have initial position that important. That means it is not a matter of concern to you where from the particle has come and where it is eventually going. You are just tracking the features as the fluid enters and leaves the control volume. So, this is called as Eulerian approach, and Eulerian approach has some obvious advantages in fluid mechanics. The advantage in fluid mechanics is that because a fluid is a continuously evolving medium, it is quite straightforward, you know, to consider a control volume in the flow and study the features around the control volume instead of tracking individual particles in the flow field. So, in the fluid mechanics courses the big challenge is how to write the equations of motion in terms of the Eulerian perspective. See, otherwise there is no big distinction in the basic laws of mechanics that govern fluid mechanics and solid mechanics, like Newton's second law of motion still you can use in fluid mechanics, but the way in which different mathematical expressions appear in the mathematical form of the Newton's second law, there you will find that because you use an Eulerian approach the form of the equation looks different, and that for a special type of fluid is nothing but the celebrated Navier-Stokes equation in fluid mechanics. In any advanced course of fluid mechanics you will find the course incomplete if we do not have a step by step procedure of starting from the very basics to arriving at the Navier-Stokes equation, and believe me or not those basics we are starting from today in this particular course. So, now the next question is that given that there is Eulerian and Lagrangian perspective, the next issue is we need to classify different types of flows. So, steady flow and unsteady flow. So, steady flow, by steady flow what we mean? By steady flow, so now we are going into the Eulerian description and trying to understand various terminologies related to that. Steady flow means the velocity of flow or the fluid properties whatever they at a given location are not changing with time. So, for example, fluid property, one of the fluid properties may be density or any other fluid property or velocity at a given location is not changing with time. So, the velocity classically is given by its three components u, v, w. U is the x component of velocity, v is the y component of velocity, and w is the z component of velocity. Okay. Now, unsteady flow is so steady means these are not changing with time. Rho is an example, it can be any property, and velocity not changing with time at a given r, at a given location. unsteady flow of course is the other thing. Now a very interesting issue is that steady or unsteady, it depends on what? Steady or unsteady, it depends on the choice of the reference frame. This is very important. Reference frame means what? Reference frame essentially means the frame from which you are looking into the motion. So if you have a situation where the frame itself is moving, then the situation may be very unique. Let me give you an example. Let us say that there is a river, on the top of the river there is a bridge and there is a boat which is moving below the bridge. So when the boat is moving below the bridge, what is happening? First of all, the water was at standstill, then the boat is coming, so it is disturbing the water, and then the boat is going away and the water is again coming to a standstill. So for the observer who is standing on the bridge, what will happen? For the observer who is standing on the bridge, the flow will appear to be what? The flow will appear to be unsteady, because the bridge is like here a stationary reference frame, and with respect to that the observer will see that there is a change in the flow that he or she is observing. On the contrary, what is happening? On the contrary, if say there is an observer, a person sitting on the boat, and the boat is moving at a velocity, at a fixed relative velocity with respect to water. So with respect to that person sitting in the boat, the same water velocity will not change with time, because the boat itself is moving at a fixed velocity relative to the water. So the same water flow relative to the observer standing on the fixed bridge will appear to be unsteady, whereas the same flow relative to an observer who is sitting on the boat will appear to be steady. So what we have learned from this is that steady or unsteady depends on the choice of the reference frame, and it is possible that you make a transformation of the reference frame and then you convert a steady flow or an unsteady flow into a steady flow by using this kind of a reference frame which is moving with a uniform velocity. So this type of transformation is called as Galilean transformation. So I am writing it down. And all the basic laws of motion must be invariant with Galilean transformation. That means the laws should not change as you make this transformation. It is still okay because you are changing the reference frame from a stationary to something which is moving with uniform velocity. So it is not changing a reference frame to something which is accelerating, it is just a reference frame moving with uniform velocity. There are two other related terminologies, one is uniform flow, another is non-uniform flow. So uniform flow means what? Uniform flow means that the velocity or the fluid properties, whatever, they at a given time are not changing with position. So this property or velocity at a given time does not change with r. Non-uniform flow means that of course this either property or velocity, these will change with location at a given time. So, the difference between these two concepts and these two concepts is that here we are freezing position and trying to see that, I mean, what is the change at a given position with time. Here we are freezing time and trying to see that at a given time what is the change from one position to the other. So, this is the difference with respect to the terminology steady and uniform. So, we have figured out the description of motion. We will come to the visualization of fluid motion in the next module, but in this module what we will try to do is to go a little bit advanced and try to see that now that we have talked about velocity, can we use this paradigm to talk about acceleration. So, the next issue is what is acceleration of flow. So, the whole idea is you have a point, at this point currently there is a fluid particle, and as per Eulerian description this fluid particle now has a velocity v which is a function of r and t. This is Eulerian description. So, r will essentially include what? Say in a Cartesian system r will include x, y, z. Remember that vector form is very generic. So, r could be anything that is described in terms of the appropriate coordinate system. In a Cartesian system only it is defined by x, y, z. So, now this is the velocity of the fluid particle. Now, let us say that the fluid particle in a small time interval comes here and its velocity at this new location becomes a function of the new position, and by this time a time has elapsed. So, it is t plus delta t. So, this is also Eulerian description. So, now what is the acceleration of flow? Let us say we are interested to find out acceleration along x. So, this is limit as delta, sorry, by definition acceleration is what? Time rate of change of velocity. So, limit as delta t tends to 0 . So, the time rate of change of velocity, the very basic definition of acceleration. New velocity minus old velocity, these are x components because we are writing acceleration along x, divided by delta t in the limit as delta t tends to 0. So, what is this? Now, here we will discuss about something which is of importance in basic calculus, which is essential for fluid mechanics. So, the whole idea is you are writing this. So, this is like a function of x plus delta x, y plus delta y, z plus delta z and t plus delta t. This we will write in terms of a function of x, y, z and t. So, what we will do is we will do a Taylor series expansion. In the Taylor series expansion, here there are 4 variables. So, the ordinary calculus, what ordinary differential calculus that you talk about, there you are having just a single variable, but here you have 4 variables. So, limit as delta t tends to 0, I am writing the Taylor series expansion of this is u x y z t plus so these are first order terms. We can keep the higher order terms in the Taylor series, but in the limit as delta t tends to 0 all those higher order terms will vanish. So, we are writing dot dot dot. So, these are all first order terms, then there will be second order, third order, fourth order, all those terms in the Taylor series. So, now I am writing here acceleration along x. So, what we will do is we will subtract these two. So, when you subtract these two, you will get so first let us write the unsteady term. So, first term is del u del t straight away plus limit as delta t tends to 0 delta x by delta t into del u del x plus limit as delta t tends to 0 delta y by delta t into del u del y and plus limit as delta t tends to 0 delta z by delta t into del u del z. So, then where are the other terms gone? These all dot 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 terms in the limit as delta t tends to 0 all those terms will be gone. So, you are left with this expression for acceleration. Now, you write this as acceleration along x this is what limit as delta t tends to 0 delta x by delta t. So, this is the delta x traversed by a fluid particle over the time delta t. This is by definition u of the particle. This is by definition v of the particle. This is by definition w of the particle. Now, the most important concept is the u of the particle same as the u of the flow? The question is yes, because as we are taking the limit as delta t tends to 0, the particle is essentially converging to that point at which we are measuring the velocity. So, the Eulerian and Lagrangian descriptions, they are merging. Okay. So that means UP becomes U, VP becomes V, and WP becomes W. So to sum it up, I am writing the expression for acceleration along x acceleration along y and acceleration along z okay. So you can see mathematical expressions, so these are just by drawing analogy with this. So it is important to know this formula, but it is more important to understand this formula physically. So what is this? This is at a given location how the velocity is changing with time, this is very clear. So this is called as unsteady component of acceleration or transient component, there may be many ways of naming it, and this is called as convective component of acceleration. So these two are two different things. So what is this? That had the fluid particle remained at the same location, but the velocity had changed at that location, then that would reflect in terms of acceleration. But there can be another component of acceleration even if the velocity at a given point is not changing with time. So in a steady flow the particle may be accelerating. So how it is possible? It is possible because the particle has gone to a new location where the velocity field has changed because it is non-uniform flow. It is steady but non-uniform, then this term is not there, but this term will be there. So the particle by virtue of migrating from one location to the other finds a new location where the velocity is different, and that is how it is getting, it is having some acceleration. So the net acceleration is the sum total physically, one, if the particle had remained at that location what would have been the acceleration, the other is had the particle gone from one location to the other what could be the acceleration. So the total effect is the acceleration. That means it is very interesting, if the velocity at a given point is not changing with time, still the particle can have acceleration because of this, that means the flow may have acceleration. In another way, even if the velocity at a point is changing with time, the acceleration may be 0. How it is possible? Let us say this is plus 10 unit, this is minus 10 unit, sum total is 0 although this is there and this is there. So all these interesting cases can be possible. Finally I will wind it up this particular module by letting you know that this is a particular notation of writing this total thing, this entire. So this is called as total derivative or substantial derivative. Why total derivative? Because it is a combination of these unsteady and convective components, and this peculiar representation comes into the picture because these are all Eulerian descriptions. Otherwise the acceleration will be simply du dt, but because it is an Eulerian description, the combined effect of time and position, that is coming up in this very peculiar way. So, this is a note, this is just a shorthand notation of writing this total derivative. So, to sum it up, in this module we have briefly introduced the Eulerian and Lagrangian description, the concepts of steady, unsteady, uniform, non-uniform flow, and we have identified a mathematical way of describing the acceleration of flow in terms of the Eulerian variables. So, we stop here in this module, and in the next module we will take it further forward from here. Thank you.